Hi, my name is Amay and I welcome you to the second part of the HTTP Request Smuggling Series. In the first video, we looked at the basics of HTTP. We learned how servers interpret HTTP requests based on content length and transfer encoding headers. Finally, we saw what happens if a request contains both these headers and if the servers fail to process them as per the HTTP 1.1 RFC. In today's video, we are going to implement what we learned in the first part by solving a PortSwigger Academy Lab on CL.TE poisoning. So let's go ahead and take a look at the lab description. The description reads, this lab involves a front-end and back-end server, and the front-end server doesn't support chunked encoding. The front-end server rejects requests that aren't using the get or post method. To solve the lab, smuggle a request to the backend server so that the next request processed by the backend server appears to use the method gpost. The first step in solving any problem is to understand it well. To understand this lab better, let's understand its architecture. Here's what the architecture looks like. You have a front-end server which is going to handle all HTTP requests coming in from users. This server then passes this request to the backend server. It is implied that the front-end and backend servers interact with each other over a persistent TCP connection. If you do not understand the concept of HTTP communication over persistent TCP connections, I recommend you to take a look at the first video of this series where I have explained this. Another important piece of information provided in the description is that the front-end server doesn't support chunked encoding. This indicates that the front-end server will ignore the transfer encoding header in HTTP requests. To solve the lab, we are required to send a request to the server such that the backend server sees the HTTP method gpost. Note that the lab description also mentions that the front-end server rejects requests that aren't using the get or post method. So if you try to solve this lab by simply sending an HTTP request with the gpost method, the front end is going to drop this request. So we need to find a way to smuggle our HTTP request with the gpost method to the backend server without letting the front end server see this request. We now understand the architecture of the lab and its objective. Now let's try to figure out how we can solve it. If you have watched the part 1 of the series, you should recollect that we have already theoretically solved this lab when we analyzed the setup of front-end and back-end servers and how they would respond to an HTTP request with both the TE and CL headers. If you haven't watched part 1 yet, I would highly encourage you to do so before continuing because I am going to heavily rely on the explanations that I have made in part 1. Now let's put our theory to the test. Let's first start the lab and pick up a random HTTP request and send it to the repeater so that we can play with it. I have picked up this HTTP request for the lab homepage. I'm going to strip down this HTTP request to the bare minimum by removing unnecessary HTTP headers so that we can focus solely on the headers that are necessary for performing a successful request smuggling attack. Let's look at the schematic from part 1 again to understand what we need such that the backend receives an HTTP request with the gpost method. So we need two separate HTTP requests. The first one is going to have both the content length and transfer encoding headers. This is the request that is going to leave the HTTP listener in a desynchronized state. And the second request is going to be the victim's request that gets poisoned. I'm going to rebuild this request manually in repeater instead of just copying them from here so that I can give you people a better context about what's going on at the back of my mind while I build the attack payload. So let's now build our request 1 and request 2 as we saw in the schematic. This is the bare minimum HTTP request that we have stripped down that we are going to play with and experiment upon. So let's call this our request 1, which is going to be the attacker request that is going to leave the socket poisoned, and we create request 2 based on the same similar request 1 that is going to be the victim request. So as you can see in the schematic, the victim request should be having a post method so that we can leave a dangling G character on the wire such that the second request, that is the victim's request, gets the method gpost. We'll come to that again later. First, let's look at the attacker request. Now, what do we need here? First and foremost, we should change the HTTP method of this request to post because we want the front end to interpret the request body and take action based on the request body. Also, we have to give it the transfer encoding and content length headers to confuse the front end and the back end. So I'm going to set the transfer encoding header to chunked and the content length header. Right now, I'll set it to 0. As you remember from part 1, the end of the headers should always be ending with 2 CRLFs, and that's why I have entered 2 new lines here. I'll enable the new line view so you can clearly see the CRLF characters in the HTTP request. Now is the time that we build our request body to kind of confuse the front end and the back end and get them in a desynchronized state with each other. So if you have seen the schematic, we have to build the request such that the front end is going to interpret it as based on the content length header, but the body of the request should be in a form that it looks like a transfer encoding header. And how does a transfer encoding header look like? Yes, you have to first start with the chunk size followed by the message that satisfies the chunk size. So I'll start with a chunk size of 3 followed by a CRLF, and then I'll add the characters ABC which satisfy the chunk size of 3 bytes. This is again followed by a CRLF. Now I want to end the HTTP request at this point. So to end an HTTP request in a chunk encoding scheme, you should set a 0 size chunk. And how does a 0 size chunk look like? You enter the number 0 to indicate that this chunk does not contain any data, and you end it with 2 CRLFs. When any HTTP parser will look at this request, and if it is processing this request in a chunked encoding format, this will be interpreted as a complete request. Now we said that we want to confuse the front end and the back end such that they don't agree with each other. So when we look at the content length header, we should set the length to the number of bytes that we want to send to the backend. So let's count the number of bytes here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So these 13 bytes will be sent by the front end to the backend, and the backend will then interpret this as a transfer encoding message and process it as such. That's because the backend is going to first look at the headers and encounter the transfer encoding headers first in order and start processing this request based on the transfer encoding header. Now, if you want to leave the socket poisoned, what we are going to do is we want, first and foremost, we want the backend to see that this is not a post request, this is a gpost request. So we want to leave a dangling G on the wire. So we end this HTTP request, the attacker HTTP request, with the dangling G, and we set the content length to what we counted earlier, that was 13 bytes plus 1, that is for the G we added right now. So we set it to 14 bytes. A small note here, whenever we are doing the CL.TE attack, you don't need to really manually set the content length size because burp repeater is going to take care of it and we don't need to set it manually, but I'm setting it manually right now for a better understanding of the concept of how this attack works. So I've set this to 14 bytes. So what is going to happen now? Let's see. the front end is going to send these 14 bytes to the back end because it is processing this request in form of a content length based request. When this message reaches the backend is going to see that the message is based on a transfer encoding, chunk transfer encoding, and it will start processing the message as such. And it will start processing message looking at the first chunk of 3 bytes, and then which is followed by a 0 size chunk, and it will stop processing the message right there. And that's when the dangling G is going to be left on the wire, which we are going to attach to the second request by immediately sending this request to the backend. Before doing that, let's look at what happens if we just send a gpost request without doing any smuggling. So you see that this is the message sent to us by the front end saying that it is only expecting get or post methods. Now let's try and send this request, and immediately after sending this request, we'll send request number 2 and see what is the error message we get. So I'm going to send this request now. We receive a response, and immediately after this we send request 2, and we have a message, a different message from what we saw earlier, that get or post were not allowed. But now this message reads unrecognized method gpost, which means that this request went past the front end, reached the back end, and the back end gave us this error of gpost. Now let's go back to our lab to see if we have successfully solved it. As you can see, we have solved the lab. So that was the expected way to solve this request smuggling lab. If you go to the lab again and look at the solution tab, you should see this is very similar to what we did, except that the solution shows a 0 size chunk right away, but we used an additional chunk before sending out the 0 size chunk. I want to show you another way that this lab can be solved even when the second request is not set to the post method. In this method, we kind of enforce the request line, and the backend ignores the actual request line that is sent in by the victim request. So to do that, we have to first create our own request line as a payload in our first request. So I'm going to add the gpost method right here, such that the backend is going to see this request line on the wire when it receives the request from the front end. And this entire part is going to be left dangling at the backend after the backend has completed processing of the above request body over here based on the transfer chunk encoding method. So what we're going to do is we are then allowing the backend to see this request line, which ideally should be followed by HTTP request headers. So it is going to expect headers to come by. And now if we send the request as is, the problem is when this request then is sent by the second user, the backend is going to see this request line again on the wire, and it's going to get confused, and it is going to return an error. That's because it expected to see headers which are of the format a text followed by, that's the header name, followed by a colon, and which is followed by certain characters, and this ends with a CRLF always. And if it does not see this pattern, and if it gets this unexpected pattern, it is going to return an error. So what we do is we show the backend that we have sent a header, but it is going to ignore it because it is not programmed to do anything with that header. It is just a random header. So I'm going to call it a random header. And I leave this out because this is going to get attached to the request from the victim's request. So the victim's request line is going to end up in front of this text, this header, the random header, causing the backend to think that this is an header, and it will completely ignore that header and process the request basis our request line over here. So now let's try and run our attack again and see if we get a gpost, the same message again, that is unrecognized method gpost. So let me send it out first. I've sent it out, and sending the request number 2, we get the same message again. So without setting this message to a post method, we still get a gpost message in the error message. That's because we are actually setting the gpost method right here in request number 1, and we are letting the backend server ignore the request line from the second request by setting a random header here, an incomplete header, because it's going to interpret this as the header value. Let's look at how this would have been interpreted by the backend. So I'm going to just paste it over here. So the backend is going to see this. So this is the second request for the backend, which then gets processed by the backend as based on the gpost method. So this is an unintended solution, but I wanted to show this to you because this is primarily used when we are doing attacks based on the TECL vulnerability. That's when the front end is processing requests based on the TE header, and the backend is doing it based on the content length header. Also, note that I did not manually set the content length in this second request. That's because, as I said earlier, Burp is going to take care of setting the content length correctly, and we do not actually need to care about this in a CL.TE attack. But when we are doing a TCL attack, the content led header becomes important, and that's when we need to manually tweak this header, and we should set the update content length here, uncheck it so that Burp does not fiddle with the request that we set over here. It is important to note that this was just a lab. In a real world scenario, this kind of attack is never going to work for you. This lab was specifically designed to be vulnerable. But in a real world scenario, you will have to hide the content length or the transfer encoding headers from the front end by setting it to a malformed value, and they can be of various types. Sometimes you add an unexpected tab character or an unexpected null byte or an unexpected space in the header name or the value, causing the front end to not see the header, but the backend is kind of parsing it in a different way, and it sees the header, which causes the parser differential, which ultimately leads to the vulnerability. That's all I have for this video. I apologize for the delay in coming out with this video, and thank you for all who commented on the first part. That motivated me to make this second part. In the next video, we will look at a TECL lab from PortSwigger and try to solve it. Conceptually, it's going to be the same, only the attack payload creation process differs. See you in the next video.